In the previous video we looked at conduction, convection and radiation. We're now going to take radiation a step further by considering black body radiation. And the first thing we need to do here is actually identify what a black body is. So a black body is defined as being an idealized physical object. So what we mean by idealized is that black bodies don't actually exist, they're not real. We can have some objects that are pretty good approximations to black bodies, such as stars, for example, but ultimately a black body is one that absorbs all of the electromagnetic radiation that falls on it. So most objects that we see will reflect at least some light, so we don't actually have any physical black bodies, but we can get some pretty good approximations to black bodies, and like I say, absorbing all electromagnetic radiation that falls on it. The word black here doesn't actually mean that it is a black object as such. It just means that it's absorbing all radiation and not reflecting any. Now if we look at a black body with constant temperature, it's going to also then emit radiation. So that's what we refer to by black body radiation. So absorbs all of the radiation that falls on it, and then it sort of re-emits that radiation, but it's not necessarily going to be in the same spectrum that it was absorbed in. So with black body radiation, we're identifying that the spectrum of light from the black body is going to be distributed according to a black body radiation curve. So the distribution of the intensity of the electromagnetic radiation is determined by the temperature of the black body. And we need to identify what this word intensity really means. Sorry, let me just finish this. So determined by the temperature of the black body. So when we look at intensity, we're basically looking at the power emitted over an area. So the equation there, I is equal to P on A. That equation is in the data booklet. They've, for some reason, they haven't used P. They've just used the word power, but ultimately it's the same thing. So here again, I is intensity in watts per square meter. P is power in watts. And A is the area over which it's distributed in square meters. So there's the equation for intensity. If we then consider the distribution of that energy, we'd need to look at a graph of intensity versus wavelength. So in graphs of relative intensity, so when we're talking relative intensity, we're not talking about the absolute scale, we're talking about how they compare to each other. So when graphs of relative intensity versus wavelength are produced, we see that there are some similarities across all of them for different temperatures. So when we're looking at different temperatures of the intensity versus wavelength, there are a few things to note. So the first is that they all have a similar shape or a similar distribution. However, there are some key differences as well. One of those is that the peak wavelength decreases with increasing temperature. So as the temperature of the black body increases, the peak wavelength, or the wavelength with the maximum intensity, decreases. And the other thing to note here as well is that increasing temperature results in an increasing intensity for all wavelengths. So they're the critical things to be aware of for the blackbody radiation curves. And the other thing there too, with increasing intensity, it also means increasing total power as well. Now when we're looking at the total power, we're really just looking at the area under the curve of the intensity versus wavelength graph. So to make a little bit more sense of that, let's actually have a look at some graphs here. So first of all, you can see on the horizontal axis we have the wavelength, and on the vertical axis we have the relative intensity. We also have 4 different temperatures represented on this graph. So there's the 4 there, 3000 Kelvin up to 6000 Kelvin. You'll notice that for each of the each different temperature, the intensity to begin with is quite low. We then have that similar shape where it increases to a maximum and then slow decrease, and then we have this asymptotic nature as the wavelength continues to increase. As well as that, you can see that the peak for each of these temperatures, so if I just put some dots in there to indicate where they are, the main thing here first of all is that the wavelength moves to the left or gets shorter as the temperature increases. Additionally, as the temperature increases, for each of the given wavelengths, the intensity has also increased. So if we choose any given wavelength, you can see that as the temperature is increasing, the intensity for that wavelength likewise increases, and that will happen for all wavelengths. Now there is a couple of equations that we need to refer to here. Now the first equation that we need to deal with in terms of blackbody radiation is known as Wien's displacement law. This is actually a fairly complex mathematical model, but we only need to deal with one particular aspect of it, which is relating the wavelength of the peak intensity to the temperature. So the equation for that is really quite straightforward, and it's basically just given by lambda max is equal to the value 2.90 by 10 to the negative 3 divided by the temperature T. So that's the statement of Wien's law that you need to be aware of for the IB. So quantities here, lambda max is the wavelength of where the maximum intensity occurs. So we're not actually dealing with the intensity as such, we're just dealing with the wavelength, and that wavelength needs to be expressed in meters. T is the temperature of the black body that's radiating energy, and the temperature is in Kelvin. That value 2.90 by 10 to the negative 3, it actually has units of meters Kelvin. That's known as Wien's displacement constant. It's in the data booklet. It's a little bit unusual that it actually includes that. It doesn't keep it as a separate symbol to represent Wien's displacement constant, but just to make sure you're aware of that idea. So there's the first law, Wien's displacement law. We can also look at the total power radiated by a black body, and that's given by a different law. So this is now identifying that for the intensity over different wavelengths, we could actually sort of sum the intensities over those wavelengths to identify what the total power is and that's going to be given by the Stefan-Boltzmann law. So the reason why it's named the Stefan-Boltzmann law is that those two scientists independently and at similar times discovered this particular law, and the equation here is P is equal to sigma A t to the power of 4. Note that I'm not highlighting that one. We need to take it a little bit of a step further. So for a black body radiating energy, P is the power that it's radiating, and that will be in watts. A is the surface area, and as is usually the case with surface area, it's measured in square meters. T is the temperature in Kelvin, and the last quantity there, sigma, is known as the Stefan-Boltzmann constant, and that value is given to you in the data booklet. The Stefan-Boltzmann constant has a value of 5.67 by 10 to the negative 8 watts per square meter per Kelvin to the power of 4. So that, again, constant that's given to you. So that's for a black body object. We've identified earlier that real objects are not actually black body radiators. So we need to take into account the fact that they're not going to emit radiation in the same way that a black body does. And so we need to incorporate a quantity known as the emissivity. And that's given by the symbol E, and so we must consider that for an object. Now this quantity itself can be defined as, probably easiest just to sort of write it out as an equation, but I'll write it in words here. It's the ratio of the radiation emitted by the object compared to what it would be if it was a black body radiator, or in other words, compared to the power radiated by a black body of the same dimensions and temperature. So that means that we can adjust the Stefan-Boltzmann law and include this property of emissivity, and so we then have the equation that P is then equal to the emissivity multiplied by the power emitted by a black body radiator, which is simply sigma A t to the power of 4. So that equation is the one that is in the data booklet, and I'll just add here where E is the emissivity. Note that it doesn't have any units, given that it's a ratio. To give you a bit of an idea, some examples of emissivity. So obviously a black body is going to have an emissivity of 1. A white body, so an object that completely reflects all of the radiation falling on it, would have an emissivity of 0. Some other substances then, things like water, somewhere between 0.6 to 0.7. Snow is about 0.9, so snow is actually a fairly close approximation to a black body radiator. Ice is even better at 0.98, and finally coal 0.95. So you can see that these ones are getting close to being good approximations to black body radiators, but still just a little bit less energy than what a black body radiator actually emits.